Next, it is still part of our AC analysis. We now look at a new parameter that we call the transconductance. Transconductance that we call transconductance of an amplifier, and the transconductance of a transistor here, we note it by GM. And this parameter in our AC analysis is defined to be IC over VT, over thermal voltage. You recall that we had got the AC collector current to be equal to the DC collector current multiplied by V BE over VT. So by isolating IC over VT, which are both DC values, they form a constant that we call GM basically, or transconductance. So we still have VBE there. So for our AC analysis, there are many models that have been developed for doing AC analysis of BJT amplifier. But for the sake of electronics 2, we've decided to use a model called the hybrid pi model. The other models that exist, in one of the most popular one that you'll find through the tutorial is the H parameter model, hybrid model. So we will study hybrid pi. We're gonna introduce H parameter, but with the only objective of showing you how to convert from H parameters to hybrid pi. So should you be given a problem in H parameters, you should just be able to convert the H parameters, because you'll be aware of them, into hybrid pi model parameters and work in hybrid pi. So our focus is on hybrid pi. That's what we're studying in electronics 2. Okay, so now when it comes to hybrid pi models, this as it stands must start by defining what is the small signal equivalent circuit of a transistor. In AC, how does a transistor behave like? What will be an equivalent circuit? So small signal equivalent circuit of a BJT. So what can you replace? What equivalent circuit can replace the transistor circuit? We know a transistor circuit is made up of 3 terminals, and that remains. So, and I want you to be very careful here and open up your ears to listen properly. When it comes, we'll look at the NPN case, and we're gonna look at the PNP. When it comes to the NPN BJT, as we go from the base, as we go from the base of the transistor, we can see through the transistor a small internal resistance that we call R pi in hybrid pi model. R pi, and I'll explain where that R pi comes from. What is the motivation for saying that there is an internal small resistance at the base, or looking into the base of an NPN transistor? It's called R pi. Then we reach the emitter. So between the emitter and the base, there is a resistance, internal resistance called R pi. R pi is caused by the following. We know that for us to achieve amplification, we have to apply a small AC voltage VBE, that in R pi model, and this is a new notation I'm introducing now, we're gonna be calling also V pi. So when you see V pi, you must know it's the same as VBE. As we apply VBE from the base to the emitter of the transistor, and due to the fact that in an NPN case scenario, a base current IB will be flowing to the base of the through the base of the transistor. Because there's because there's IC that we've established to be IC VBE or V pi now, because it's the same thing over VT, or else written as GM V pi. Now we can have IB which is the AC base current, which is still related to the AC collector current through the DC current gain, which is beta. So that will normally give GMV pi over beta. One will also see it as IC over beta V pi over Vt, which would lead to the DC base current multiplied by V pi over Vt. So that's an alternative. You should be able to manipulate these formulas and use the parameter that you have at hand. That's also a very important skill in doing AC analysis. But the fact that there is, when you apply a certain voltage from the base to the emitter, you get the current to flow through the base. That means by Ohm's law that there must be a resistance, and that's what we call R pi, which is the resistance measured from the base of a NPN of a BJT transistor to the emitter. It's internal to the transistor, which is caused by V pi or VBE divided by IB by Ohm's law. So that's how we came up with R pi. So now, as you reach the emitter, and IB flows this way into the emitter, you get to the collector side, and on the collector side you normally have a current source, which is IC basically, which you've established to be GMV pi, which supplies the collector current. And here I'm talking now about the AC collector current, and that goes to the collector like that. So the collector side is represented by current source. Why? Because inherently in a transistor, as we said, it's a transconductance amplifier by default. So you apply VBE, you get IC. So you can still convert the IC in a voltage for you to get voltage to voltage, but naturally it's first VBE to generating current. Okay, so now very important, we stick with that for now. We go to PNP. In the PNP case scenario, as we know, IB flows from the emitter now to the base. But before we go there, let's just remind that there's also an emitter AC current, IE, which is still IB plus IC. Right, very important. In a PNP case scenario, the small signal equivalent circuit will be, if you start with the base, of course, it's fine. You still have a resistance R pi, but that resistance R pi is caused by by the voltage V pi or VBE being applied between the emitter and I think I'll just draw it differently so that you can picture what is going on here. And this time around, I'll go from the emitter. So I'll go with the configuration where you've got the emitter and you've got the base and you've got the collector, which is a PNP transistor. Right. So as you go from the emitter to the base, because as you go from the emitter to the base, because in a PNP, VBE or V pi is normally applied from emitter to the base. The emitter side is on a higher voltage potential with respect to the base. You also have a resistance. This time we're gonna call it an internal resistance is here, which is called RE this time, and till you reach the base. Now, RE is caused by a current which is IE, by the IE current. So IE is the emitter current flowing there. So the presence of IE and VBE creates RE, which is therefore VBE by Ohm's law divided by IE. Now, as you reach the base, the IE splits into IB on one end, as well as IC, which is the collector current, which now, because remember, Kirchhoff's current law must be satisfied. Since IE is coming this way, IE must split into IB and IC. So IC is going that way, which means the current source on the output side of the transistor AC equivalent circuit will be pointing up now. As you come out on the collector, you've got IC going that direction. So that will be the small signal AC equivalent circuit of a PNP. That will be the one of the NPN. Very important. And we've established two very important internal resistances here, Re and Rpi. So it doesn't mean that there is no Re here, and there's no Rpi here. There's still an Re in an NPN, because it simply means that will be the resistance as measured, the internal resistance of a NPN transistor is measured from the ammeter. That will be Re, which is still caused by the same voltage of VB or Vpi, divided by, but a different current, which is IE. So Re is still V pi over IE. So how does Re, the same way here, there's still R pi, which is the internal resistance that you would measure from base to the emitter, looking into the base of a PNP. And that is still caused by VBE and a different current, which is IB this time instead of IE. So how does R pi relate to RB? The fact that IE is higher than IB, and they are both caused by the same voltage, V pi or VBE, that will mean automatically that Re will be smaller than R pi. Remember, the higher the denominator, the smaller the overall fraction. So, but how are they related? Re is V pi over IE. We also know that IE is beta plus 1 IB. That if you isolate V pi over IB, you're gonna get R pi, of course, divided by beta plus 1. So R pi at the end of the day is actually equal, which is the same equation as R pi being equal to beta plus 1 Re. So that is what leads to another type of AC analysis model that we call the T model, that I'll also briefly introduce here, because that's the model that Glob's Basic Electronics uses, T model. But it's quite similar to the hybrid pi that we are using here in our analysis.